Hello, dear viewers. Within the framework known as the string theory landscape, we encounter a profound synthesis of string theory and cosmic inflation. This framework proposes a multiverse consisting of many pocket universes, each with different physical constants and laws. The concept of a finely tuned universe is central to understanding why the string theory landscape has attracted so much attention. Fine-tuning means observing that some fundamental constants and quantities in our universe, such as the mass of the electron, the force of gravity, and the amount of matter, lie within a very narrow range that allows the existence of life. Deviations from these exact values can prevent the formation of complex structures such as galaxies, stars, and ultimately life itself. This brings us to the multiverse hypothesis proposed by string theory medium. If we accept the existence of multiple universes in a multiverse, each with potentially different physical constants, the fine-tuning of our universe may no longer appear as a singular improbability, but as an inevitable outcome across a multitude of different universes. This anthropic principle suggests that we observe such fine-tuning because only universes with such conditions can accommodate observers. String theory proposes that the fundamental components of reality are one-dimensional strings, not point particles. These strings vibrate at different frequencies and in multiple dimensions, beyond the familiar 4 dimensions, giving rise to the particles and forces of the standard model of particle physics. Cosmic inflation, on the other hand, is a theory of the early universe that proposes a period of rapid exponential expansion immediately following the Big Bang. This theory explains the remarkable uniformity and flatness observed in the cosmic microwave background radiation. String theory originally arose to address the complexities and limitations of particle physics, proposing that the fundamental components of the universe are not point particles but tiny strings whose vibrations determine particle properties such as mass and charge. As theoretical physicists explored these ideas, they realized that the equations governing string vibrations could have many solutions, each corresponding to different physical realities or space. This multiplicity of possible solutions gives rise to the concept of landscape, the theoretical space of all potential universes allowed by string theory. It was not easy for string theory and cosmic inflation to converge within the framework of the string theory environment. Initially, these theories followed parallel paths. String theory focused on the very small, subatomic particles and fundamental forces, while inflation focused on the very large, the structure and evolution of the universe. The integration of string theory and cosmic inflation came about when theorists began to see how string theory could potentially explain the mechanism behind inflation. The landscape of string theory, which proposes a multitude of possible vacuum states, each corresponding to a different set of physical laws, constants, and structures, provides a natural framework for a universe undergoing inflation in various regions, leading to physically different outcomes. This synthesis has been controversial. Critics argue that multiverse theory is a speculative construct that deviates from empirical science because it predicates the multiverse as a theory on the existence of areas beyond observational or experimental reach, making it virtually unfalsifiable. The idea of landscape helps explain why certain physical constants in our universe, such as the cosmological constant or the masses of fundamental particles, appear to be finely tuned for life. In the multiverse scenario proposed by landscape, each universe could have different physical laws resulting from different solutions of string theory equations. Therefore, the particular laws of our universe are not necessarily unique or inevitable, but it is one set of possibilities. Imagine playing a game where you throw darts at a board covered with countless small, differently colored areas. Each region represents a different set of rules for how to play the game. Many times your darts will land in a zone where the rules do not allow for a fun or playable game. But because there are so many possibilities, there are a few areas where the rules work perfectly to allow for great gameplay. In this analogy, our universe seems to hit one of those rare regions. The crux of the debate boils down to the nature of physical laws. Traditional views, supported by physicists such as Einstein, emphasized a universe governed by a set of laws that were both universal and discoverable through careful scientific investigation. These laws were thought to be succinct, reflecting the simplicity and beauty that many physicists believed underlie the workings of the cosmos. On the contrary, proponents of the string theory environment argue that while the basic mathematical formulations of string theory are simple and elegant, the actual physical manifestations of these equations open up a wide range of possibilities. This perspective introduces a level of complexity and variability that fundamentally challenges the classical view of an ordered universe. An important aspect of the landscape hypothesis is its potential explanation for the fine-tuning of certain physical and cosmological parameters that appear to be specifically configured to support life. The cosmological constant is the best example of this. This parameter is critical because its surprisingly small value allows the existence of stars, planets, and eventually life. Conventional physics has struggled to provide a satisfactory explanation for why such a value needs to be so finely tuned. Landscape theory offers a probabilistic solution. If multiple universes exist, each with different physical laws, as part of a larger multiverse, then it is not surprising that at least one of them, ours, has life-conducive parameters. This reflects the statistical consequence of having multiple universes. Andre Linde's comments highlight how the string theory landscape can potentially rationalize various fundamental constants and conditions in our universe, such as the similar masses of protons and neutrons, the relatively small mass of the electron, and the peculiar three-dimensional spatial structure of our universe. However, the adoption of the string theory environment is not without its detractors. Critics argue that if physical properties vary significantly across the multiverse, then trying to understand certain features, such as the weakness of gravity in our universe, may be futile or even misleading. Moreover, a theory that posits multiple unobservable universes challenges the very nature of what constitutes scientific inquiry. If a theory does not make testable predictions, can it still be considered part of empirical science? Shamit Kachru's words underscore a broader philosophical and practical concern in the physics community: the fear that adopting such a framework could diminish the search for a more fundamental understanding of physical laws. Imagine a big city with thousands of restaurants. If someone is looking for a very specific type of food, say a rare Ethiopian dish, they can find it in a big city because there are so many options. Similarly, in a vast city of universes, it is not surprising to find at least one universe, like ours, where conditions are suitable for life. Or imagine walking into a vast library where each book represents a different universe. Each book has its own rules. Some may describe worlds where gravity is stronger, others where particles have different masses, and still others where the dimensions of space vary. This library is similar to the string theory landscape, which suggests that all these different books or universes are possible outcomes based on the equations underlying string theory. Just as a library has books containing various stories, landscape also has universes with various physical laws. Also, consider the analogy of a lottery to illustrate the idea of fine-tuning, specifically the cosmological constant. Imagine that you have to choose a number from a very wide range, say 1 to 1 trillion, and there is only one winning number that allows you to get the prize. The probability seems astronomically low, but if there are millions of people playing this lottery, it would be less surprising if someone eventually won. Similarly, if there are countless universes, each with different values of the cosmological constant, it's not that surprising that at least one of them, our universe, has the right value that allows stars, planets, and life to exist. Leonard Suskind's analogy comparing humanity's understanding of the expanding universe to the acceptance of the multiverse encapsulates a broader narrative of scientific humility and progress. Just as humanity is gradually accepting that the Earth is not the center of the universe, we can also accept that our universe is just one of many. Thank you for listening. Stay well.